All right. So this chapter is about vectors, as you can see from the title. So let me motivate this first. So in physics, we'll deal with quantities like this. Okay. So we'll deal with these quantities: velocity, acceleration, forces, momenta, linear and angular momentum, and all that. Speed, pressure, temperature, distance. Besides the physical difference, I mean, that's a huge difference. Do you see any difference between these guys? Any mathematical difference between these guys? Okay. To specify pressure, how many numbers do you need? One. To specify speed, how many numbers do you need? Pressure, no, speed, temperature, one. All these guys need one numbers to specify them. Okay, so you can specify these quantities using scalars. Scalars are quantities that have one number to them. How about these guys? I'm sorry? Okay, so you need magnitude and direction, so we'll come to that. Okay, so same thing again, magnitude and direction. Okay, magnitude and direction. Okay, so these are quantities that you need more than one number to specify. Okay, so now let's come to the direction part. Okay, so let's okay, so we all understand that. Let's say I can apply a force in this direction. Okay, and so the force is being represented by a vector. Okay. The length of the vector is the magnitude of the force. Okay. And now, see, to specify this direction, what you really need is two numbers. Okay, so here's a projection. Okay, so we'll define, now the two angles can be defined in many different ways. Okay, here's how we do it in physics. Okay, we define this one angle of the vector from the z-axis, and then, so if this was the x-axis, y-axis, and z-axis, there's the z-axis, but it can be anywhere along that plane. So you need another angle to specify it. Okay. Okay, so you need this angle as well. Okay, and this angle is called, we call it phi in physics. Okay. All right, so you see, for these guys, to specify the angle, you really need two numbers. Okay. So to specify these quantities, what you need is three numbers. Okay. Okay, so these quantities are represented by vectors. Yep. So vectors are sort of a different sort of mathematical beast than numbers, than scalars. Okay. And we'll study the properties of vectors in this chapter. Okay. So this is a new kind of mathematical quantity. Yep. And whenever you learn about a new mathematical object, what do you learn? What do you want to learn? How do you learn about this new mathematical object? I'm sorry?
Use it in an example.
So what you'll want to first learn is how to add them, subtract them, multiply them. Just like you did with numbers. Yeah, and that's what we're going to do. Yeah, so that's your goal today. Yeah, to learn about how to add, subtract, and multiply vectors. Yep. All right, so how many numbers do you need for vectors? 3 numbers. Okay, so it turns out that in n dimensions, you need n numbers. Okay. One for the magnitude, and how many numbers for the direction? I'm sorry? Okay, so it's n, you need n numbers. So you've used one number for the magnitudes, and minus one, very good, my friend. Okay. So if you're in 4 dimensions, you need 3 numbers for the direction, okay? All right, but we are dealing with 3-dimensional vectors, so we'll use 3 numbers, okay? All right, so everybody understand where we're going? Yeah, all right. So here's the notation, okay? Vectors will be denoted like so, okay, with an arrow on top, sometimes with a bold letter, okay? When you see this notation, that's telling you the magnitude of that vector, okay? So that's giving you that one number, okay? Vectors will be denoted by directed line segments, okay? So directed meaning this vector is pointing in that direction. The arrowhead tells you in what direction it's pointing. Okay? The length will be proportional to the magnitude. Okay? Here are vectors drawn in how many dimensions? 2 dimensions. So all you need is 2 numbers. Okay? And so there's the magnitude is proportional to the length, and the other number is the direction. Okay? All right. So here's an example of a physical vector. So this is a displacement vector. A displacement vector is a vector that points from your starting point to your end point. Okay? So let's say you went on a walk like that. There is your displacement vector. You went for this walk. There is your displacement vector. Okay? You went for this walk. There is your displacement vector. Okay? So how many different paths have the same displacement vector? An infinite number of paths. Okay? So the displacement vector is sort of like an average sort of thing that says. It doesn't tell you any details about what your path was. Anyway, so that's the displacement vector. So that's a vector. Okay? All right. Okay, so like I said, so vectors are a new kind of mathematical quantity, and you want to learn how to add and subtract them. Okay, so let me start off by showing you. You guys know how to add numbers. Okay. Did I do it right? All right, so here's a vector A, and here's a vector B. All right, now one property about vectors is, you can move the vectors parallel to itself, and there'll be this vector is equal to that vector. As long as their magnitudes are the same and they're pointing in the same direction, these vectors are the same. Okay? So let's say I want to add A and B. So here's how you add A and B. Okay? So you draw the tail of B to the head of A, and the sum is this guy. This guy is A plus B. Okay. So here's how you add vectors. Yep. Any guess on how you would subtract these vectors? Yep.
Reverse the direction of B and add
Okay,
seven.
so our friend there said, and see, that's a very logical guess. So when you're subtracting 2 things, you're really adding the negative of B. Okay, so you just have to learn how to define B, a negative B, and our friend there said this is negative B. Okay, All right, so here is A, and here is negative B. Okay, and so this is A minus B. Okay, so you know how to add and subtract vectors. Okay, except that we've done this graphically, and this is not a very practical way to do calculations. Okay, so we want to learn to do better. We want to know how to algebraically add and subtract vectors. Okay, and that's what we're going to build towards. Okay, so before we do that, let's do one more thing. Okay. So here's A. Okay, what do you think 2A is? I'm sorry? What do you think it is? Double the length. Okay, very good. Yeah. That's a good guess, right? And what is minus 3A?
3 times the line that goes in a different direction.
That's right, in the opposite direction. So this is minus 3A. Okay. Now, without realizing it, here's what you did. Okay, so this was a vector. What was this guy?
The scalar.
It's a scalar. So you multiplied a scalar with a vector, and you knew what that meant. Okay, so we'll remember that. Okay. All right. All right. So here's A. 2A is that. Minus 2A is that. You know all of that. Okay. So we already talked about this. This vector is equal to this vector. Okay. They have the same length, and they're pointing in the same direction. Okay. So what this means physically is, let's say you're driving 70 miles an hour north on I-95, 70 miles an hour north on Nova Road. Your velocities are the same. Okay. The only difference is on Nova Road you're getting a ticket for that. All right. All right. Here are two vectors. To add them, all you do is move the tail of the first on the head of the second. Again, there is B. Okay. And that's how you add them. Okay. Do you know how to add three vectors?
One and then put the other one, the third one at the end of the.
There you go. See? Do you know how to add 100 million vectors? Yeah. Okay. So once you know how to add two vectors, you know how to add no matter how many vectors, right? All right. So 1, 2, 3, 4, 5, and there's the sum. Okay. All right. Now here's another thing. Whenever you learn about a new mathematical object, so now today we're learning about vectors, then you'll learn about matrices and stuff like that. Okay, and you always start off by doing that. You learn how to add, subtract, multiply them. Okay. So one of the things we want to learn is, see, you know that 4 plus 5 is the same as 5 plus 4. Okay. Okay, it's commutative under addition. And you want to see if that's true for vectors as well. It turns out it is true. Okay, so here is A plus B, and this is B plus A, and the sum is the same. Okay, so vector addition is commutative. Okay. It's also associative. What that means is, I mean, we do this every day and we don't even realize this. 4 plus 5 plus 3 plus 7, it doesn't matter how you add them, okay? The order of addition doesn't matter. Okay, so 4 plus, okay, we'll just do with 3. Is the same as 4 plus 5 plus 3. which is the same as 3 plus 4 plus 5. Okay. And that's the same, that's true for vectors as well. Okay. So if you're adding 100 million vectors, you can add them in any order you want. You'll get the same answer. Okay. We already know what the negative of a vector means. Subtraction is just adding the negative of that vector. Okay. All right, any questions so far? Scalar yep, go ahead. Oh, I see, okay. We already saw that multiplying a scalar to a vector, what that means. Okay, it just, so what does this mean? Yep, half as long. All right. All right, now we're going to introduce 3 special vectors. These guys are going to be your best friends. Okay? All right, so these are unit vectors, okay, and they'll point along the coordinate axis. So here's the x, y, and z. And you'll see different notations in different books. So x hat, y hat, and z hat, and so on. Okay? I like to use I, j, and k, so we'll use I, j, and k. Okay? Before I do this, now, so let's say A is a velocity vector. What are the dimensions of A? Dimensions are length over time, so meters per second. Okay, those would be the units, SI units. If A were an acceleration, what would be the dimensions? Meters over second squared. If A were force, it would be kilograms meters per second squared, which is equal to newtons. Okay? All right, depending on what the physical quantity is being represented, its dimensions will be different and the units will be different. Okay? These guys are dimensionless. Okay? So unit vectors I, j, and k that we are introducing are dimensionless, and their length is 1 unit. Okay? So that's the property. So unit vectors are dimensionless vectors of magnitude unity. Unit vectors along the x, y, z axes are denoted by I, j, and k. So these special unit vectors, we'll call them I, j, and k. Okay? How many different unit vectors are possible? I'm sorry? How many different unit vectors are possible? So unit vectors are vectors of dimension 1, or magnitude 1. There are an infinite number of unit vectors possible. Right? All right. We just are particularly interested in these 3 guys. Okay? All right, now let's, so what is I? What is I? Is it a scalar or a vector? I'm sorry? It's a vector. What is J? A vector. Vector, okay? Be careful. What is this? 5i, what is that? It's a vector, okay? You multiplied a scalar to a vector, and that's a vector, okay? And help me out. So here's the x-axis, okay? 5i is this vector, okay? How about 6j? Is that a scalar or a vector? Vector, okay. Now what we'll do is we'll add the 2. Okay, so there is 6j. Okay, you know how to add vectors, so the sum is from the tail of this guy to the head of that guy. Let's give it a name, A. Okay, so what you have done is you've written a vector A in component form. This is called the x component of the vector. This is called the y component of the vector. Okay? And the reason we do this is the following. So now let's define another vector, 3i plus 4j. Okay, and you guys know what that is. Okay? So you go 3 units in the x direction and 4 units in that direction. Okay, that would be b. Okay. So let's draw that. There is b. Okay. And now a plus b is as simple as this. It's just 5 plus 3i plus 6 plus 4j. Okay. It's that simple. So now you've learned how to add vectors. Okay. You guys understand that? All right. What would A minus B be?
Across the
Axis,
Uh,
x-axis.
I'm sorry?
Oh, flip the across the x-axis.
So B minus B would be minus 3i minus 4j. And then if you add that, it would be, so 5 minus 3i plus 6 minus 4j. Okay? Everybody understand that? Okay. Now you guys are good, so I'm going to give you a slightly more complicated thing. Okay? What did I just write? A 3-dimensional vector. Okay? So it has a x, y, and z component. Yeah. So you just do component wise. Okay? The x component of this plus 2 times the x component of that, and so on. Okay? So the rules are simple. So 3 plus 2 times 4i plus 4 plus 2 times minus 7j plus minus 5 times 2 times 2. Okay. All right. All right, so now you see the point of writing vectors in component forms. Okay? Now you can do algebra very easily. Okay, so now you've learned how to add and subtract vectors. What else is left? Multiplying vectors, and we'll get to that. Okay? Yeah. All right, so I, J, K are unit vectors. They are dimensionless. Okay, and the reason that is dimensionless is 5i. Okay. This is 5i. So this, if this were a velocity, this guy is dimensionless. The units are contained there, meters per second. So it's 5 meters per second. Okay, if this were an acceleration, this would be 5 has the dimensions of meters per second squared. Okay, so we are going to use the same I, j, and k for different physical quantities. It's the components that'll have the dimensions. Okay, so that's why we use dimensionless unit vectors. Did you guys understand that? Okay. All right, so here's a vector A. This vector is this vector plus that vector. AX is the x component of this vector, AY is the y component. Okay, so here in this diagram, I is represented by x hat, y hat represents j. Okay? So there's the x component, there's the y component. Okay? Now, when you're doing algebra, so when you add, subtract, and multiply vectors, what you want is to write vectors in this component form. Okay? Are these the only two ways to specify the vector? No, you can give magnitude and direction. Okay, you can give the magnitude, the length of the vector, and this number. Okay, so the vector A can be specified by giving you these two numbers or these two numbers. Okay, right? In 3 dimensions, if the vector was in 3 dimensions, let me know if you guys understand this. Okay. You could give these 3 numbers, or the vector could be specified by giving its magnitude and these 2 angles. You guys remember those 2 angles from the diagram before? Okay. All right, so you're specifying the same vector using 2 different sets of numbers, so they must be related. Okay, so if you're given these numbers, you should be able to calculate these numbers, or if you're given these numbers, you should be able to calculate those numbers. Okay. So before we do that, does this set of numbers have more information, or does this set of numbers have more information? They should have the same, right? Logically. Yeah. All right, so we won't do 3 dimensions yet. Okay, so we'll show you the relationship between, we'll show you the relationship between these 2 guys in 2 dimensions, okay? All right, so given these 2 numbers, to get to that, so given the components, the magnitude is the components, given the components, there's a magnitude. And given the components, the angle is calculated like so. Theta is tan inverse of AY over AX. Okay? So given these numbers, that's how to calculate those. This is the formula you use. Given these 2 numbers, to calculate that, this is how you do it. AX is A cosine theta, and AY is A sine theta. Okay? And to use these formulas, here's the rule. The angle is measured from the x-axis counterclockwise. Okay? So what we're saying is the following. So if this is the x-axis, this is the y-axis, and here's a vector A, the angle theta is that angle. Okay. So AX is A cosine theta, and AY is A sine theta. Okay. All right. So what this slide is telling you is the following. If you have a vector in this quadrant, the vector will have both positive, I'm just making up numbers, both positive x and y component. Okay? A vector in this quadrant has negative x component and positive y component. a vector in this quadrant has negative x and y component, positive x and negative y. Okay. All right, so we already know this. To add two vectors, write the vectors in component form. This is A in component form, this is B in component form. And then to add them, you add similar terms. So you add the x components and you add the y components. Okay. All right, so let's do, so you understand that. So what does this mean? So this would mean ax plus 3bx minus 5cx I plus ay plus 3by minus 5cyj, and if it has a z component, az plus 3bz minus 5cz. Okay. Okay. So now you know how to add, subtract vectors. Okay. Everybody understand this? Any questions on that? All right. We still only have learned how to add and subtract them. Okay? So we'll learn how to multiply them soon. All right, so again. Okay, so what this diagram is telling you is the following. So here's this vector A, and if your coordinate system is like that, there's the x component of A and there's the y component of A. And here's the same vector. Now if you use this coordinate system, okay, its components are different. So A is 5i plus, I'm just making these numbers up, okay? 6j, or 3i prime plus 7j prime. Okay? So these refer to a different coordinate system. Did the vector change when the components change? No. Okay? So the choice of the coordinate system is the language you're speaking in. The language you're speaking in, should that change the laws of physics? No. All right. So the laws of physics will be written like this. It'll be written like, so this is an equation that we'll see in the next chapter. What this is saying is, this is the final position vector is equal to the initial position vector plus velocity times time plus 1/2 acceleration times time squared. Okay? So a law of physics will say this vector is equal to that vector. And if you say write this vector in Spanish, you'd better write this vector in Spanish too. Okay? And that will be true. So if you write this vector using this one coordinate system, you write this vector in the same coordinate system. All right, let's look at this equation a little more closely. Okay, so on this, so laws of physics are generally given as equations, mathematical equations, and we already know some properties about mathematical equations. Okay, so if you have a vector on this side, can you have a scalar on this side? No, that would be apples to oranges. Okay, so if you have a vector on this side, you'd better have vectors on that side. Okay, So here on the right-hand side, we have sum of three terms. So each term had better be a vector. Well, this guy is a vector, so we're good. What is this guy? This guy is a vector. T is a scalar, time. Okay. A scalar times a vector is a vector. Now we're good. T square is a scalar, half is a scalar. That times a vector is a vector. So vector plus vector plus vector is a vector. Okay. So now what you've learned is, if somebody gives you an equation like that, that's not a good equation. Okay. So you already know this. Okay. So you can already tell a correct equation from a wrong equation. Okay. This is what Einstein is famous for. Okay. All right, so this is called a tensor of rank 2. So if you want, it's a 4 by 4 matrix. Okay. Each element being a function. Okay, so here's a 4 by 4 matrix. Here's a 4 by 4 matrix. A scalar multiplying a 4 by 4 matrix. And that's equal to a 4 by 4 matrix. Okay. So if Einstein had written that, you wouldn't be talking about him. Okay. What is the problem with this? This is a 4 by 4 matrix. Now they're adding a 4 by 4 matrix, and that's a scalar, that's a number. Okay, so you guys understand? Okay. So this is a rank 2 tensor, a vector is a rank 1 tensor, a scalar is a, very good, my friend. All right. What happened to that fella?
He's too smart.
Huh?
He's too smart.
Shh. And I told him not to miss a class, right? We'll give him an F. What do you think?
Yes.
Yeah, there you go. All right, now we'll learn how to multiply vectors. All right, when it comes to numbers, there's only one way of multiplying them. Okay. Vectors are slightly more complicated, and it turns out that there are two ways of multiplying them. Okay. So one product is a scalar product, and the name comes from the answer is a scalar. So in 3 dimensions, how many numbers do you need to specify a vector? 3. Okay, so you're going to take 2 objects, 3 numbers, and the answer is going to be 1 number. Okay, so you're going to start off with a more complicated number, you're going to multiply them and get a simpler object. Okay, so a scalar product. And the other product is a vector product. As the name suggests, the answer will be a vector. Okay, so let's look at the 2 products. All right. I'm sorry?
Vaguely familiar with it from computer science.
Okay, right. Yeah, I mean, you'll need linear algebra, and so you can see that in there. Okay. All right, so here's a vector A, here's a vector B. Now you want to draw the vectors from the same point, so the tails are at the same point. This is the angle between them. And the scalar product, it's also called the dot product because of the notation. This is the notation for the dot product, scalar product. A dot B is defined as the length of A times the length of B times cosine of the angle between them. Okay. This is a scalar, scalar, scalar. So that's a scalar. Okay, so you started off with 2 vectors, and the scalar product is a scalar. It's a number. In physics, you'll see the work done by a force is a dot product, the force dotted with the displacement vector. Okay? And so it'll be F d cosine theta. Okay? So you will use it there. Okay? And that's one place you'll use it. One of the places you'll use it. Okay? Here's another way to define this dot product or scalar product in terms of components. Okay? So A dot B is ax, bx. The components are scalars, so that's a scalar, plus a scalar is a scalar, plus a scalar is a scalar. Okay? So you end up with a number. Okay. So here's the dot product in terms of components. Here's the dot product in terms of the magnitudes of the two vectors. And you'll be using both the formula. Okay? Any questions on that? Vector product. Okay? So now the result will be a vector. All right, so what we're going to do is we are going to multiply these two vectors, A and B. Okay? So since the result is a vector, let's call it C. Okay? And here's the vector, here's the definition. Okay? And I can, have you guys done determinants yet? How many of you have done determinants? Yeah, don't worry about it. You've done it? No. You don't need to know this, but I'm just writing it down in case you've done it. Okay? All right, all you need to know is this definition. Okay, so A cross B is AYBZ minus BYAZI. Okay, and you'll use it enough times that you'll remember it, and even if you don't remember it, you'll just look it up. Okay, so AZBX minus AXBZ. J. Okay, so here's the pattern. The x component of the resultant vector of C, the x component, doesn't involve x component of A and B. The y component of C doesn't involve the y component of A and B. The z component of C doesn't involve z components of A and B. Okay? Let me show you how to remember this. Okay. So let's draw I, J, K. Okay. So A cross B, when you're writing the x component, so you're going cyclically. Okay, when you're writing the x component, it's AYBZ. Okay. It's AYBZ. And then negative of the flip, AZBY. Okay, plus, now you're going to write the y component. The y component would be AZBX. Again, don't worry about it. What is the second term? I'm sorry? Very good. Plus the z component. Help me out here.
AXBY.
AXBY. Okay.
And then AYBX.
Very good. Okay. So you see, you took two vectors, multiplied them, and got a vector as a result. Okay. Now this has the unusual property, okay, just to show you, it is a different beast. What is 4 times 5? Is equal to 5 times 4, right? Well, A cross B is not equal to B cross A. In fact, it turns out to be equal to negative B cross A. Okay. So this vector product is a different product, different sort of product, okay? All right, so this vector product is important enough where I'll give you the product for, again, let me draw the I, J, K. Okay, so I cross I is 0. Any vector crossed with itself turns out to be 0. And that's easy to see because if you take the same vector, this would be AY, AZ minus AZ, AY. Every component will be 0. Okay? So any vector crossed with itself is 0. I cross J equal to K, J cross, again, cyclical order. Okay? J cross K is I, K cross I, J. I cross K, negative J. Very good. Okay. All right, so you know how to cross multiply unit vectors. Okay. Okay. So now that you know that, you could use that trick to find cross products as well. So 5I plus 6J crossed with 3I plus 4J. This would be 5 times 3, 15. I cross I is what? 0. 5, I cross J is K. So 5 times 4 is 20, K. You following me? Okay. And so J cross I is what? Negative K. So it's 6 times 3 is 18, negative 18K. Okay. J cross J is 0. Okay. And so that's 2K. All right. So finding cross products that way also is easy. Okay, here's what I want you to notice. Okay. Where is this vector? I'm sorry? It's in the XY plane. Okay? So let's call this A. So A is something like that. And this is B. Where is this guy? It's pointing along there. Okay, so the cross product is perpendicular to the plane that's containing A and B. Okay, and that's a general rule. Okay. So the cross product always is perpendicular to those two vectors. Okay. Now in physics, in physics 2, you learn the force. This is a charged particle. Q is the charge, V is the velocity. The force on a charged particle moving in the magnetic field is given by the cross product. Okay? And you learn torques are given by cross products. Okay? So this is the point, this is the position vector of the point of application of the force. There's the force, and that's the torque. Okay? So that's why we learned this kind of stuff. All right. Do you have any questions? So the lecture portion is done.